Hi, what's on our workbench today is a ZOYI ZT-701 oscilloscope and multimeter combo. It was sent in from Zotac. As usual, I will leave a product link in the video description below for those who are interested in getting one after watching this video. There are a lot of these oscilloscope and multimeter combo devices on the market today, and I have reviewed quite a few of them over the years. What is unique about this ZT-701 is that it's actually very compact. It is roughly the size of a small power bank, and is very portable. Of course, given the small size, there are some compromises that had to be made, and we can see that from the specifications. For instance, the multimeter is a 10,000 counts one, and it does not offer any current measurement modes. Also, the included oscilloscope is only rated up to 5 MHz bandwidth, with a sampling rate of 48 megasamples per second. So the specs are quite modest, but what you get in return is this tiny pocket-sized device. The meter feels quite solid, and it has this rubberized bumper along the sides, so it should be able to take some moderate abuse. It comes with a soft instrument pouch, a pair of leads. By the way, the tips of these leads are not gold-plated. And it also comes with a charging cable. Now, what is interesting is that it also comes with a stick-on stand. Let me just show you here. So this is very interesting, as the instrument itself does not have a stand-on. So I'm not sure why they don't just mold it as part of the case. Nevertheless, if you want a stand, you can actually stick it on if you'd like to. And by the way, there's a safety interlock shutter at the bottom of the case. It covers the USB port while the sockets are exposed. And if you need to charge the device, you just need to slide it over. You can see that now the negative side is covered and the USB port is exposed. Now the shutter is a little bit stiff, as you can see here, but it does work. This is actually necessary as explained in the manual, because the oscilloscope and the charging circuitry share the same ground. And if you were allowed to do measurements while the device is being charged, you would create a very dangerous situation if you connect the negative leads to something that is not at the ground potential, and it could blow up your meter and possibly your connected device. So in my opinion, regardless of whether or not your meter has this interlock feature, it's always a good idea to disconnect the charger first before doing measurements. Anyway, let's plug in the leads and do some measurement. I just took the leads out. You can see that indeed these were not gold-plated. And by the way, these are right-angled leads. Now, for meters with the sockets on the side, I do wish they supply with some straight leads. But anyway, that's a minor issue here. So let me plug it in. Now let's power it up. The power button is on the side. By default, it boots into the multimeter mode, but you will remember the last mode you were in. For example, let's actually switch to the oscilloscope mode, and to do that, all you need to do is this button here. You can see it is called auto/mode. So you press and hold it. You will switch to the oscilloscope mode, and let's actually power it off and see if we boots back into the oscilloscope mode. So let's press and hold. Oh man, I'm not sure if you saw that. I think I spotted a typo in the shutdown message. It says shuts on. Anyway, let's power it back on and see if it changes back to the oscilloscope mode. Yep, you can see that we now booted into the oscilloscope mode instead of the multimeter mode. Anyway, let me change it back because we're going to start with the multimeter testing. And I think ZOYI had done a great job, as it's very easy to navigate around. You can use these arrow keys, for example, to change to different measurement categories. And within each category, you can use the menu key to change between the subcategories of measurements. So that's very intuitive. The meter also has the min-max, average, and frequency as the secondary display. Now, in this multimeter mode, when you long press the menu, you can see that we can actually change the orientation of the display from portrait to landscape. And I guess some people probably prefer one orientation over the other, but for me, it doesn't really matter that much. Now, interestingly enough though, in this horizontal display mode or landscape display mode, we don't have the secondary display here. And I think it's a pity, because there is probably enough space for Zotac to add the display in. Of course, they may have to shift the layout a little bit. Or if they don't want to add the secondary display, at least make the main display a little bit bigger, as this font actually is the same size as the font in the portrait mode. It would be nice if they make the display bigger. It will make it easier to read. And by the way, I just realized that I still have the screen protector on. Actually, let's fix that first. And let me change it back to the vertical mode. And we'll do some measurements. Now I hold it up to my MV216A voltage standard. Let's actually start with the millivolt range. Let me switch to millivolt. And you do see that we actually have some residual value. And to route it out, all we need to do is short press the power button here. And you can see that right now it is routed out. And by the way, in DC voltage measurement modes, whether or not it's in millivolt or in volt range, the accuracy is specified as 0.5% plus 3 counts. In the lowest 10 millivolts range, which is the range we're in here, the resolution is at 1 microvolt. So let's see if we can register a microvolt. And let me dial in 1 microvolt. 1. Yeah, you can see we are able to register something here. 2, 3, 4, not bad. 5, 6, 7, 8, 9, 10. So that you can see with this meter, we are able to discern the changes of a single microvolt, which is very good. Of course, because the least significant digit is 1 microvolt, that's why we're seeing it jumping around a little bit. That's perfectly normal. Anyway, let's do 1 microvolt at a time. Let's change it to 0 here. And then let's do 1, 2, 3, 4. You can see that it's pretty responsive. 5, 6, and the readings are relatively accurate. 7, 8, 9, 10. Now, of course, is over range because it's slightly above the 10 microvolts reading. All right, now let's move on to the volt range. And this is the 10 microvolts that we just put in. Let's actually clear that. And let's do 1 volt at a time. 1, 2, 3, 4, 5. You can see that the update rate is actually pretty good, and the reading is definitely within spec. 6, 7, 8, 9, 10. Now let's take a look at the AC voltage measurement. For that, I'm using my Unity UT61E Plus as a reference, and both meters are measuring the output from a Variac. So let me crank up the voltage, and let's take a look. And you can see that the update rate is fairly fast. Let's keep increasing. And readings are agreeing with one another. You notice that for the Unity meter, when the voltage increases above 30 volts or thereabouts, it displays this warning symbol. And for the ZOYI, we don't see any warnings just yet. So let's keep increasing. And let's keep increasing again. It seems that on the Zotac, the warning started displaying after 100 volts. And let's change it to the maximum. And you can see that readings between these two meters are largely in agreement. Now, because we only have a 1% accuracy on this meter, so the reading is definitely within spec. And also, you probably have noticed that on the Unity UT61E Plus, we have one extra digit, and that's because this is a 22,000 counts meter versus a 10,000 counts meter. And once we go above 100 volts, the display on the ZOYI drops to a resolution of 0.1 volts. And also notice that the bar graph update rate is not that particularly fast. I propped up the meter a little bit, so hopefully it's easier for you to see. Now, it's always tricky to get the angle right because of the lighting above and also the reflected screen here. Now, it would be ideal if I actually propped it up even more, but the problem you can see here is the leads here are in the way, so they actually slide down. Anyway, all right, let's do our next measurement. And that would be diode. The first one we're going to measure is a standard silicon diode. And you can see that we are able to measure the forward voltage drop with no problem. Notice that there's no beep, indicating that it's a good PN junction. Now let's change to a different diode here. And let's go straight to a white LED. You can see we're able to light it up and also measure the forward voltage drop. No problem. Next, let's do continuity test. And you hear that the measurement is definitely latched. And it's actually reasonably fast. It's just unfortunate that these leads are not gold-plated, so the contact is not that great. but no problem at all. Now, you also notice that the display update is not very fast. In fact, it lags quite significantly behind the sound here. So eventually it catches up, but you cannot rely on that to determine whether or not there's continuity. All right, let's move on to ohm measurement. And let's first actually rail it out. Remember, the rail button here is the power button. And we're jumping all over the place because these are not gold plated, so let's try it again. And that's close enough. Well, maybe not. Let's do it again. Okay, so now let's first measure a 100 ohm precision resistor. This one is with a 0.1% tolerance. And we're close enough. Remember, the resistance measurement mode only has an accuracy of 0.1% plus 3 counts, so this is definitely within spec. And next, let's measure a 1.25K precision resistor with 1% tolerance here. And let me remove the rail. Okay. And no problem. Let's move on to capacitance measurement. Now, if you recall, some of the meters we tested recently having trouble measuring small capacitance in the picofarads range. So let's actually first test out whether or not we can register a 10 picofarads capacitor. Now, we do have some residual reading, but I'm not going to clear it out. Let's just try to measure it. So here is a 10 picofarads capacitor. Let's give it a go. And you can see that we do have some residual. The reason I didn't want to clear it out is because it depends on the leads position. The readings are jumping all over the place. But right now, let's say we have roughly 18 or 20 picofarads reading. So we should get 30 something. And we do. You can see that we are able to measure that 10 picofarads capacitor here. Very good. And let's try another one. This time, let's do a 22 picofarads. So again, we should be reading around 40 something. And we are. So this ZT-701 is able to measure very small capacitance down to picofarads range. And now let's do a 100 nanofarads capacitor. And no problem. And if you recall, this one actually is consistently lower than the 100 nanofarads nominal reading. So this one is largely in the ballpark. And now let's try it with a 1 microfarads capacitor. Yeah, no problem. For the next test, let's go straight up to 15 millifarads. And of course, it will take some time. Are we able to measure? Yep, we are. So you can see that we get a 14 millifarads reading, which is no problem. And now let's briefly take a look at the oscilloscope mode. And in oscilloscope mode, just like in multimeter mode, you can also change the orientation of the display. Now, that is not done by the manual button, but in this mode, it's actually done by briefly pressing the power button. So let me show you here. And you can see that now we change it to horizontal. In oscilloscope mode, the display is actually quite comparable, except that the manual now is on the side. Of course, for today's testing, we're going to use the portrait mode. So let me press it again, and we'll change it back. Currently, I'm generating a test signal from the UTG-962E. And the signal is a 1 kHz 1 volt peak-to-peak sinusoidal. Of course, we don't have anything displayed on the scope yet, and that's because we haven't really acquired the signal properly. So let's actually do that. To auto-acquire the signal, you can see here we have a button, auto mode, and we short press on this button. And it's doing acquisition. The auto acquisition is actually quite fast. Now, I don't know why. Okay, so that horizontal line disappeared. And the signal is not all that stable. You can see here it is wobbling a little bit. I wonder if that's because I'm touching the... Oh, right now it's more stable now. So I'm not sure. And yeah, you can see it is not entirely stable. Anyway, while we have this waveform displayed, let's actually take a look at the controls. Now, after playing around, I can tell you that the controls are actually very intuitive. For example, right now, if I press left and right, you can see that we're changing the time base. And if I press up and down, that is changing the attenuation. If I press the menu button, you'll see that now we change to this move submenu function, and now I can use the arrow keys to move the waveform around. You can see here. And of course, if I press it again, now it's trigger, so I can actually adjust the trigger level. So very intuitive. Of course, the next one is AC/DC. You can see that is a coupling. So now if I press the up or down button, you'll see that it changes to DC. And we also have additional menu items to select from. And to activate that, you just need to long press the menu button. You can see now we have, again, the first one is coupling, as we had just seen before. You can also change it here by up and down. Now it's AC. And we have the trigger mode. You can do auto, normal, and also single. Very good, it even supports single shot, which we'll definitely take a look at a little bit later. And we have the rising edge, falling edge triggering, and we have, what was that? More measurements. So let's actually turn it on. Okay, so now you can see we have the min, we have also the RMS value and the duty cycle. Very good. Also forget, you can actually take a screenshot in either multimeter mode or the oscilloscope mode by press and hold this button here. This button is called hold and save. So in multimeter mode, you short press it, it holds the display, but when you long press it, it actually takes a screenshot. All right, now let's increase the output frequency from the function generator and see what kind of bandwidth we're getting. So now let's see here, sine wave, and let's do 10 kilohertz. That's well within the bandwidth, and let's acquire the signal. And let's do 100. No problem so far, which is to be expected. And let's keep increasing to 1 megahertz. And let's do it again, 1 megahertz. You can see that we're a little bit wobbly here, and also the peak-to-peak dropped to 0.8 volt. Now, that may have nothing to do with the bandwidth here. That's because we have this long leads, and also the impedance matching is not ideal. Let's increase 1 megahertz at a time. 2, 3, 4, 5. So this is at our specified bandwidth limit. Let's reacquire the signal. And you can see that we're still able to see the signal, but it's jumping quite a bit. And there's some kind of artifacts going on here too, as you can see. And the signal quality is definitely not ideal. But we're still within that 3 dB bandwidth from a peak-to-peak voltage perspective. And let's do 6 megahertz. From the sampling rate perspective, I think it is able to handle much higher frequency, as some of the scopes with the same ADC, 48 megasamples per second, claims to be able to handle up to 10 megahertz. But of course, sampling rate is not the only factor affecting your bandwidth. It is also determined by your front end as well. Anyway, let's just keep increasing and see what we get here. Right now, you can see we're already at 3 dB bandwidth. Let's do 7 megahertz, 8. Yeah, you can see that we're not able to capture that waveform cleanly anymore. Right now, you can see we're measuring a 1 megahertz square wave, and the waveform is not very stable. It's jumping all over the place. But the rising edge and falling edge, the edges are actually quite sharp. So let me increase the frequency a little bit. 2, 3, yeah, you can see here. Let me reacquire signal. The edge is becoming more round. That's because we have higher harmonics and the bandwidth is only at 5 megahertz. Let me actually change it to 1 kilohertz and see if we get a more stable waveform here. So the compensation here, I think, is definitely hit or miss, as I would expect at 1 kilohertz, the rising edge would be sharper, but you can see here is a little bit rounded, and that's because of the frequency compensation of the amplifier inside. Now, there's no way for us to adjust as we only have these probes here. How about 100 kilohertz? And you can see that 100 kilohertz, we're able to capture the square wave pretty cleanly. Now, it's still jumping around and also has some artifacts going on here. And here I have an amplitude modulated signal. The modulation frequency is 100 Hz at 100% depth. And the carrier frequency is only at 100 kilohertz, but we're not able to stably acquire that signal. You can see that I can change the time base. Here you sort of see the envelope, but as I decrease the time base, you can see that we're not able to see the modulation envelope. And if I increase it, You kind of can see it is an amplitude modulated signal here, but we're not able to get that characteristic envelope here. Now I reduce the carrier frequency to 10 kHz. Now you sort of can see the modulation envelope, but the frequency is actually quite low. And now I change the modulation to frequency modulation with the same 10 kHz carrier frequency. And the modulation frequency currently is at 100 Hz with a frequency deviation of 1 kHz. And you can sort of see it is being frequency modulated, but again, if I change the time scale here, you can see that we're not able to definitively capture that frequency modulation. And here's a single shot capture measuring the output characteristics of a power supply. And you can see that we're able to capture the power on waveform. All right, time for us to open it up and take a look inside. Now you're looking at the current consumption of this meter. In oscilloscope mode, we're currently drawing about 230 milliamps, and given a 1.5 amp hour battery, you can comfortably run it for over 6 hours. So that's actually not bad. And let's actually change it to multimeter mode. And we're drawing actually less. So we're drawing 200 milliamps. And in multimeter mode, you can actually run this for more than 7 hours. And now we're in, and it's somewhat what I had expected. There is not too much going on in this meter. We have quite a few relays here, that's to switch between the different ranges, and we have a single microcontroller, and it's handling both the oscilloscope and the multimeter functionality. And here, that's our voltage reference. And the part number is ICL8069. We actually don't have any dedicated ADC for the oscilloscope, so that actually explains why the oscilloscope performance is quite poor. And if you take a look, there's really not too much going on here. This one is a EEPROM, and not much more that is on the side of the board. And I'm not expecting anything on the other side, except for the display and the keypad. Of course, we have the shielded section for the input, but I don't think there's anything fancy, so I'm not going to bother removing the shielding can here. Overall, the ZT-701 is just a budget pocket multimeter and oscilloscope. The multimeter implementation is quite solid, and the oscilloscope is probably adequate for viewing and capturing basic waveforms. Some people may find the omission of the current measurement a deal breaker, but that is actually a deliberate choice by Zotac, so that they can keep the size of the multimeter small. Let me know what you think about this meter in the comment section below. Anyway, I hope you enjoyed this review and teardown. If you liked the video, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.